Hi, everyone. My name's Yuyuan. I'm advised by Professor Ming at University of Wisconsin-Madison. And today, I'd like to introduce our research project. It's an NVMe-over-TCP profiling utility that can help us understand and profile the NVMe-over-TCP protocol. Nowadays, disaggregated storage is widely deployed. Storage disaggregation is a system infrastructure that separates compute resources from storage resources. In this architecture, nodes with significant computational resources, such as CPUs, are referred to as compute nodes, while nodes equipped with extensive storage resources, such as SSDs, are called storage nodes. Compute nodes and storage nodes are interconnected via the network. The compute nodes can read from and write to the remote SSDs if they were local. To enable storage disaggregation, the remote storage protocol is essential. It defines how I/O requests and responses are transmitted. There are many transmission protocols, such as NVMe over Fabric, iSCSI, Fiber Channel. Among them, NVMe over Fabric is the dominant one that is used to manage NVMe drivers. In this project, we focus on NVMe over TCP protocol, which is a popular family member of NVMe over Fabric. NVMe TCP is a high-performance protocol that carries NVMe commands to the remote NVMe subsystems via TCP/IP fabric. The network packet transferred in the Ethernet begins with the Ethernet header, followed by the IP header and the TCP header, and then the PDU, which is the protocol data unit. PDU is the basic data transmission unit in NVMe over TCP. A PDU can carry I/O commands, data payloads, or control status. There are 5 types of PDUs in total to transfer data. Here is an example of PDU that carries the data sent from the data node to the compute node. Before explaining how NVMe over TCP protocol works, let me first introduce 3 key definitions. First is the initiator. Initiator is the client that sends NVMe commands over a TCP/IP connection to access remote storage. It is typically located on the compute node. Second, target is the server that receives and processes the NVMe commands, providing access to its local storage resources. It's on a storage node. Third is the NVMe TCP session. That is the reliable bidirectional communication channel established between the 2 sides. Here is an example of a data read operation. First, the initiator sends a read command to the target. Second, the target executes the command and transmits the requested data back to the initiator. This process may involve multiple transmissions. Third, once all the required data has been sent, the target sends a completion message to the initiator. The case of writing I/O is similar, but it depends on the size of the write I/O. Given that NVMe TCP is widely deployed, it's essential to understand and profile how it works. While the protocol itself appears straightforward, its implementation actually is introduced significant complexities. The goal of this research is to understand how NVMe TCP works and develop a utility to profile it. Now let me introduce the challenges of understanding and profiling NVMe over TCP. We focus on the implementation of NVMe TCP over Linux. The first challenge is that the request execution path is very long, which involves many subsystems. Let's continue with the data read example. First, on the initiator side, the application submits a read I/O request via the system call to the blockMQ subsystem in the block layer, which is in the kernel space. Second, there is a kernel module called NVMe TCP. The blockMQ will forward the request to the protocol handler in it. We call this layer the NVMe TCP layer. Third, the protocol handler generates a PDU carrying the read command, The PD is first inserted to a request buffer, then moved to ascending queue. Next, the PD is copied to the TCP socket buffer within the NVMe-TCP session, which resides in the TCP network stack layer. And the command is then transmitted over the network to the target on the other side. The NVMe-T TCP module is the target kernel module. It reads the commands from the TCP socket buffer and passes to the protocol handler in the NVMe-TCP layer there. The protocol handler extracts the command from the PDU and submits it to the block MQ in its block layer. And then the block MQ will submit the command to its local NVMe subsystems. And finally, the IO is executed on the SSD. The completion path is similar, but on the opposite direction. Finally, the block layer on the initiator side returns the data to the application. As you can see, the data path is very long, and it involves multiple kernel subsystems. Issues can happen in any layer, slowing down the execution. In addition to this, the diverse I/O profiles and the parallel I/O execution path adds to the profiling difficulties. So how can we use existing solutions to understand and profile the protocol? Typically, people have to manually profile from multiple layers and then synthesize the results. For example, for a database developer, what if they found the database running slow? What can they do? They may first turn to tools like DBbench, which will show the end-to-end latency and throughput. But it's not detailed enough. Next, they may try tools like perf to see CPU usage, memory footprint, thread hotspot. However, it contains too much information, and it's hard to focus on the NVMe-over-TCP parts. In addition, these issues may be on the remote side. The synchronized analysis adds difficulties. Later, they may use low-level infrastructure utilities like iperf, qperf to validate if underlying network fabric satisfy the deployment assumption. But we still need to synthesize the results on both sides, on multiple layers, to localize the issue. As we can see from this example, these tools operate across different processes. Significant effort is required to align timestamps and detect potential issues. Additionally, these tools collect large volumes of information specific to its own layers. This makes it difficult to identify the most relevant data to focusing on. To address this issue, we propose ntprof. ntprof is an adequate profiling utility that dissects NVMe-over-TCP execution characteristics. It can break down software processing overhead over the I/O path. It enables us to analyze how NVMe-TCP protocol interacts with the underlying storage subsystems. It can help developers to locate bottlenecks when running atop NVMe-TCP-based disaggregated storage architecture. Our goal is to make this tool informative, profiling-rich, and lightweight. The key idea to design ntprof is to model the NVMe-TCP as a network and then apply network monitoring techniques to profile it. In the data path of NVMe-TCP, as we have seen earlier, there are multiple stages represented by those gray boxes. We model each stage as a software switch. Specifically, we have 9 software switches here. Alternatively, we can draw the system overview in this way. There are 9 stages along the I/O path. Thus, the I/O path of an NVMe-TCP submission or completion response consists of a chain of switching queues. Next, to analyze those switching queues, we use Linux tracepoint mechanism. A tracepoint is a static instrumentation point within the kernel that exposes a hook to call a customized function. For example, in here we define 2 trace points. QRQ is triggered when the block I/O enters the enters stage 2. And try-send command PDU is triggered when the command leaves, exit that layer. To collect statistics, we are inspired by TPP, a proactive network monitoring system. ntprof issues special I/O requests to collect runtime statistics. Upon triggering a trace point, ntprof creates, updates, and seals a profiling records based on the registered function. For example, ntprof can record a trace point table of an I/O. We can define the hooked function to append an entry to the table, which is the timestamp and the trace point name. Let's say the red triangle is a read I/O. When it enters the NVMe-TCP transport stage, the trace point is triggered and append a record to the trace point table. When it exits the stage, another entry is appended to the table. These statistics can be used for further analysis. After collecting the trace points information of the special I/Os, we use a MapReduce-like processing to generate the results. For example, when we have multiple trace points collections of read I/Os already, then the analyzer will categorize the results by its size if it is specified by the user, and then use aggregation function to generate results such as latency, average latency, or tail latency on a specific stage. To use the ntprof to profile, the first step in the workflow is that the application developer defines the profiling specification, which includes what type of I/O to profile, the size of the I/O, the type of the I/O. And step 2 is based on the profiling specification, they configure ntprof. And then the application developer runs the application, for example, a database system. Step 4 is to collect the profiling results using ntprof. And step 5 is to generate the report based on the collected results. For example, the latency breakdown or I/O latency distribution. We then use multiple use cases to evaluate ntprof. We used 2 SM100P nodes in Cloud Lab. The bandwidth of the NIC is 100 gigabits, and there are 4 NVMe SSD on each node. As for implementation, we modified kernel source in NVMe-TCP and NVMe-T-TCP kernel modules to define and add additional trace points. We also implemented 2 kernel modules, one on the initiator side, another on the target side, and a user space utility in C. We used both synthetic and real-world application to evaluate ntprof. I will show one use case in detail. In this use case, ntprof breaks down the latency of 4 kilobytes random read of NVMe-over-TCP requests. As we can see, when we increase the FIO depth from 1 to 32, the end-to-end latency increased significantly. ntprof shows more details. As we can see in this breakdown, the time spent on the target side for I/O execution is increased, but only slightly from 65 microseconds when I/O depth is 1 to 82 microseconds when I/O depth is 32. However, the network part increased a lot, from 14 microseconds when I/O depth is 1 to 126 microseconds when I/O depth is 32. It includes the TCP/IP stack and the network transmission. But the network bandwidth is not saturated. The throughput achieved when I/O depth is 32 is about 300 megabytes per second, but the bandwidth of the network can be as high as 12 gigabytes per second. The increased latency in this part is caused by queuing buildup in the network stack, which where the requests are waiting to be transmitted. ntprof identifies this by modeling the I/O path as a chain of software switches. It defines 2 trace points on the execution path and another 2 on the completion path, which allows us to break the end-to-end latency down. We also explored additional use cases, including software bottleneck localization, where we intentionally constrain the TCP connection on the target side, and hardware bottlenecks, where we introduce contention on the SSD and the NIC. These experiments demonstrate that ntprof can effectively detect queuing delays and pinpoint performance issues. Additionally, we show how ntprof enables interference analysis by running latency-sensitive and throughput-sensitive workloads concurrently. Under mixed I/O traffic, ntprof generates distinct profiling records to capture relevant statistics, making it possible to analyze workload interference. Finally, let me summarize my presentation. NVMe-TCP is a predominant protocol for storage disaggregation, but we lack an adequate profiling tool for systematic understanding. While existing solutions are tedious and inadequate, people have to profile on multiple layers and synthesize the results manually, which is very hard. To address this issue, we propose an adequate NVMe-TCP profiling tool called ntprof. The key idea is to model NVMe-over-TCP as a network. Through synthetic and real-world application use case study, we show that ntprof enables different I/O profiling tasks, including latency breakdown, software, hardware bottleneck localization, and interference analysis. The implementation of ntprof is open sourced. And thank you for listening. Feel free to ask any questions.